Awesome. Thank you, Adriana. Thanks all for having me here. It's a pleasure. My talk is going to be a bit of an outlier. I'm going to talk about post-reconstruction stuff. And the big motivation is my goal is to make some of these methods practical. And as those who work with list mode data or projection data know that they're some of the largest data sets that we do have, which are in terms of data size are best suited for AI models, are also pure images. We have lots of image only cohorts, no raw data available for large swaths of data that are out there in the medical image community. I think some of these post-recon methods are really useful for making those accessible and useful for AI. All right, so my interest is in PET imaging, and let me make sure okay. So when I talk about post-reconstruction enhancement, mainly I'm talking about two different problems. One is resolution recovery. The other one is denoising. Specifically for PET, low resolution is a product of multiple sort of effects. Some of them are hardware related, some of them are software related. Noise, on the other hand, often arises in a lot of situations, some of which Simon was describing in his talk earlier, where we can have very short scan times, we can have low radiation dose. Either of those would lead to very noisy images. And the situation that I will generally cover in this talk involves going from image domain to image domain, where we start off with a corrupt image, which could be either blurry or noisy, depending on whether we are trying to do a super resolution problem or work with a denoising type problem. And in both cases, the goal is to generate a clean output directly from the image domain. So broadly in the medical image enhancement field, like we've had this very rough timeline that we have shown, I'm showing here, where we have, let's say about 6 to 8 years back, we saw a lot of CNNs coming up, and initially it was shallower CNNs, and then we transitioned to deeper models. And eventually the UNet, which was proposed for image segmentation, became the default choice as an image generator network, which is also what it's used a lot today. At some point, we saw GANs making an entry, and they're still going strong. We use them a lot, give very robust results compared to a pure CNN-only format. And then I would say in comparison, transformers made a bit of a later entry. They came to language first, sort of got adapted to vision, but by now we have a lot of well-optimized structures that tend to, despite their data-hungry nature, seem to work well for medical imaging. In a bit of a parallel, sort of, it's not a one-on-one sort of match there, but in the initial years, we saw a lot of emphasis on fully supervised architectures. These are cases where we have paired training data. We have labeled data sets, we have clean images, corrupt images, we can learn the mapping. But then over time, we saw a lot more of emphasis on sort of unsupervised cases, including both sort of weakly supervised cases where we may not have paired examples, as well as self-supervised cases where we are directly trying to learn from these corrupt images and figure stuff out from there. So in the context of super resolution, I'll sort of go over two scenarios. The first one is the sort of the lower hanging fruit, where we have paired images for training. So we have low resolution images, high resolution images. We're trying to learn the mapping. The slightly more difficult situation arises when we do have two different cohorts corresponding to low and high resolution, but these may not be matched images. We still have data to work with, but it's a much harder mapping to learn. So some of the earliest work we did in this field, this was my then PhD student, now postdoc Juan Song, who developed a very deep CNN for super resolution using paired data. A very deep CNN back in 2019 when we did the work was a 20-layer CNN. So the paradigm has greatly shifted with that disclaimer. This was essentially a 20-layer network. The inputs were patch-based. We worked with the low-resolution PET image as an input, but in addition, we also had anatomical guidance from a high-resolution MR image In PET, resolution is spatially varying. So we also provided, since we were working with patches, we also provided radial and axial coordinates as additional inputs to the network. We did fairly extensive comparisons with these 4 inputs. This is the V4 architecture that I just described. We had other combinations of inputs. We compared with shallower architectures. These are about 2 to 3 layer networks. We compared against paired deconvolution, penalized deconvolution, partial volume correction. This is the low-res image we started with. This is the target high-res image, and this is what the method gives. And if you look at these magnified images, the visual quality was closer to the high-resolution ground truth. And even in terms of benchmarks like PSNR and SM, this method outperformed all these other competing methods. So with that, we moved on to a slightly more complex problem where we have 2 different cohorts, one low resolution, one high resolution from 2 different scanners. So we were looking at data from the Siemens HR Plus, which is a legacy scanner. At that point, it was still being continued to use to be used in many locations because of longitudinal data acquisition protocols that were already in place. So this was one of the bigger motivations. Generally, in these scenarios, oftentimes the high-res images are degraded to match the resolution of the lowest resolution image that's available in, let's say, a multi-site study. And so methods like this would have the advantage that you don't have to degrade your images. Anyway, so again, for this setup, you're looking at paired images, unpaired images being used for training. And so for this work, we developed a generative adversarial network-based architecture. And so the goal is to go from the low-res domain to a high-res domain using this generator network. And I'm going to talk a little bit more about it shortly. But then we don't stop there. We map this result back to the low-resolution domain using a second generator. And both of these results are checked using discriminator networks. The first discriminator network does an unpaired check. So it checks in the distribution domain, whereas the advantage of this sort of going back to the low resolution domain means we can now check at a pixel level, pixel to pixel check. So because now we can compare the original low resolution image with the synthetic low resolution image to check for inconsistency. And so even for this work, we did several comparisons against several variants of this method. So one of the key pieces of this work was the introduction of this split generator mechanism, where one part of the generator is based on a pre-trained simulation guided network. And this was key essentially because the low to high resolution mapping is a hard problem. And so putting in the additional feature generator that's trained on simulated paired data sets provided it an added level of robustness. So we did comparisons against the case where there was no simulation guidance, as well as a third case where we did this mapping from high to low resolution using an analytic blurring step. And so relative to all these methods, we saw both improvements in both visual quality and PSNR and SIM. And that we also actually tested an unsupervised method, which was recently published at that time. And our method went very close to the supervised gold standard. So fast forward to 2026, and the HRRT, which was our high resolution standard for all these works, is no longer the sharpest scanner in the block. And so we started working with some NeuroExplorer data recently, and you heard about total body PET earlier in this session. And the NeuroExplorer is a long axis field of view scanner, which is designed specifically for neuroimaging. It generates very high sensitivity and spatial resolution. Here's a picture of a prototype. This is just a visual example of how close the PET image looks compared to sort of a T1 weighted MR image in terms of overall sharpness. And this particular image was from the SNMMI 2024 Image of the Year that presented NeuroExplorer results. So for here, our goal was to start off with HRRT data and try to match it to the image quality of the NeuroExplorer. And to do that, we utilized this data set, which consisted of paired NeuroExplorer and HRRT images from 7 subjects corresponding to 7 different tracers. And for each tracers, there were 2 different time windows, so effectively 2 sets of images per subject. And as you can see, the early and the late time window, they look quite different in terms of noise level. This is the early window from the NeuroExplorer, early window from the HRT, late NeuroExplorer, late HRT. And these are just the FDG scans, but in the original case, we had multiple tracers. Now, the goal here being for us to develop a mapping from the HRT domain to the NeuroExplorer domain. And our intent is to apply this model to other data sets, so to make it generally deployable. The challenge is, as you may understand, that this is a very small data set. And then if we were to train a model using this data set and apply it to other data sets, we would run into challenges posed by domain shifts, because there would be looking at a different population, different imaging protocol, different contrast levels, and so on and so forth. And so my student Zhou has been working on this project, and he created a self-supervised contrast-aware PET super resolution network with deep degradation guidance. Now that's a mouthful. Let's just call it DDG-SR. So this network essentially consists of two parts: a super resolution SWIN-IR transformer model and a degradation autoencoder model. So this is the transformer part that maps the low-res image to the high-resolution domain. And then the autoencoder, it maps this SR image back to the low-resolution domain. And I'm going to talk about how to train this network. And so this is sort of done in a two-part way. The first part uses just the training data set that I just described, where there's paired data available. So stage 1A, the first part of the first stage, involves directly training the SuperRes transformer with the paired training data. And in the second part, we train this degradation encoder decoder, but this is trained in self-supervised mode using the corrupt images alone. However, there is also sort of guidance from the high resolution directly to the decoder, and you'll see when I put the network together why this is useful. So in the second stage, we actually fine-tune on the target data set. So if you have a data set from a different scanner, a different application, this is where you would take the previous model and try to fine-tune that. And so what gets fed into this SR transformer includes a mean and standard deviation image that gives slightly more specific information about the contrast and noise in the images, anatomical guidance. All of that goes into the transformer. Note here that a part of the transformer here is frozen, a part of it is trainable. It produces the SR PET image, and then this SR PET image gets fed directly into the degradation decoder instead of what we were where we were feeding in the high resolution image during the first training stage. And ultimately, all of this is kept frozen during training. We only adapt part of the transformer that generates the SR PET image in this adaptive stage, where we fine tune and make it work for a different previously unseen data set. So for testing, we used images from the Alzheimer's Disease Neuroimaging Initiative. There's a public data set. We had a mix of different disease stages: cognitively normal subjects, subjects with mild cognitive impairment, and a few subjects with Alzheimer's disease. And similar to the previous training data set, there were two different time windows, but the windows were not matching. These are both, it's based on FDG PET data, but the window positioning is different, and so the image quality is quite a bit different. So different contrast levels and uptake patterns. And so we did comparisons of this model with a traditional UNet as well as a standalone SWIN-IR that has not been adapted. And here are some sample images. First and foremost, the NeuroExplorer images provided here. These are unpaired, just to give you a sense of the visual quality. This is the input ADNI HRT image. This is what the UNet produces. This is what the transformer produces, and this is what DDG-SR produces. As you can see, you see more variability in each of the regions with the adaptation. Before adaptations, the images, each of the regions look very flat. So we would have an image very similar to the SWIN-IR image. The DDG-SR process introduces more variability in the individual regions. And so we also looked at contrast to noise ratios in several regions that could be meaningful for FDG quantitation, and all of them, this method outperformed the other two approaches. Since this was implemented in 2D, we also looked at other the other sections, sagittal and coronal sections. Original training was done in using transverse slices. We only had used cognitively normal subjects for training. We looked at MCI in Alzheimer's disease patients as well. We also did a little bit of statistical analysis on the results. For some of these regions that I reported, we had a significant improvement in the CNR, and this is a subject-wise distribution of the CNR in the results. So with that, I'm going to switch gears and talk a little bit about denoising, which is yet another image enhancement setup. And so a lot of the early work on image denoising focused on, again, a paired setting where we have low noise and high noise examples for training. And then there have been a lot of methods that have evolved that only operated on low count images. So you only have the corrupt images for training your model. We did some early work on that topic using this noise to void model that we published back in 2021. The idea was that instead of using all of the voxels that are available to us, we mask out everything around the central voxel which we are trying to estimate. And by forcing the network to learn from neighboring voxels without knowledge of the target voxel, you avoid having a trivial solution, and so you end up trying to make your best guess, and your model ends up learning. So anyway, this was the noise to void method, but for today, what I'm going to talk about is multi-tracer and multi-scanner denoising. This is something we're very focused on, mainly because in PET, many of these supervised models that we have seen in the context of denoising work extremely well for one tracer, one scanner. They do not generalize very well. So our goal, and we started off, it's not a, right now we don't have a huge cohort, but we are building to it. Our goal is to sort of eventually make an all-purpose denoiser. And so our objective is therefore to create a generalizable model that works for multiple tracers and multiple scanners. Again, this was work by my student Yuan Zhou. So he created the dual branch gating diffusion transformer, DGDIT, which was published in TRPMS last year. The two main components of this network are a variational autoencoder and a diffusion transformer. This figure is a little bit dense, so let me just mention the basic concept to you. So we heard quite a bit about diffusion models earlier in the presentation, I believe in the first session. Diffusion models are expensive to run. One of many workarounds that have been proposed, one of the sort of general pathways that are quite appealing are to use a latent space approach, where instead of trying to run this very expensive diffusion process on the whole image, you first map the image to a lower dimensional compact representation, and then you run your diffusion pipeline in latent space. So that leads to cost savings. And then the other idea is therefore here to, so we do the VAE there just to do that mapping so you can create a compact representation. The other idea here is that instead of a unit, we replace the basic denoising unit inside of the diffusion model by a transformer that gives it additional representation capabilities. So here too, we use a two-stage training approach. So in the first step, we train the VAE, and that essentially involves learning a mapping from the original image domain to the compact latent space, and then trying to map it back. And in this reverse sort of step, you provide the noisy image and any anatomical information you may have as conditional inputs to the decoder as it reconstructs the final image. Then in the second stage, that is where we train the diffusion pipeline. And so during this stage, we hold this encoder. We keep it fixed. We freeze those weights. We train the diffusion model. We also simultaneously train a conditional encoder that works on these conditional inputs. And so for training and validating this model, we used a 3-tracer, 2-scanner data set also from the Alzheimer's Disease Neuroimaging Initiative. So these are just some example images. Importantly, we actually compared this against a wide range of state-of-the-art techniques, including some transformer-based approaches, diffusion-based approaches, and convolutional approaches. So these are results from the HRT with FDG, and then HRT with fluor-beta pair, which tracks amyloid, HRT with fluor-taucipir, which tracks tau in the brain, and then the same tracers with the Siemens Biograph, so FDG, fluor-beta pair, fluor-taucipir. So in terms of metrics like PSNR and SSIM, this method very consistently outperformed all these other competing methods for all the tracers and all the scanners. And we also looked at CNR in several key brain regions where DGDIT was also a consistent winner. And also kind of to check how well it performs in out-of-domain data sets, we applied this to C11 PIP. So that's a different radioisotope, essentially noisier images. Also amyloid, but the PIP distribution can look markedly different from for beta pair. So here too, although the PSNR dipped for all of the methods, here too, the DIT approach was the winner. So with that, I just want to share some concluding thoughts, specifically for sort of the post-reconstruction enhancement setting. I think we'll see a lot more, and we will also need a lot more innovation for a lot of specific scenarios. One thing that I want to highlight is the need for more blind single image super resolution techniques. It's very hard to model the exact PSF in PET, depending on your protocol, depending on your tracer. There could be a lot of variation in PSF measures, and so blind methods can be very attractive, in my opinion. We've also seen a lot of new papers arise on noise-aware and contrast-aware denoising. These, again, are ways to make these methods more flexible and useful for a broad range of data sets. We're obviously seeing a lot of interest in non-FDG radio tracers, so the go-to tracer for training majority of AI models has obviously been FDG because that's where you have the largest data sets. But as we develop more models, I think the interest is gradually shifting to other tracer types, and it's going to be increasingly important. I already mentioned the need for having models that will help us not have to degrade images to match quality for cross-site. So the cross-site harmonization is also another place where post-reconstruction enhancement is particularly important. And in general, task-based validation is one of those, I guess, those topics that we keep running into because it's very important, clinically speaking, to sort of go beyond images that look beautiful and can ultimately prove useful for specific clinical tasks. And we've seen a lot of foundation model applications recently that have been used for specific clinical targets. We hope to see more large models being sort of fine-tuned for image enhancement applications. Here's some reviews that we wrote with some folks in my lab that cover some of the general approaches, survey of approaches for image enhancement for PET, and the other one is for PET and SPECT. I believe since the more recent one is 2026, some of the methods that I covered are not even part of that review, so a little bit old. But with that, I wanted to thank my wonderful lab members, thank my funding sources, and thank Chris and Andrew for having me here. Thanks all, and happy to take questions.